3.5 talks about summary of curve sketching. So the guidelines for curve sketching, we look for domain, we look for intercepts. Symmetries, kind of sort of. Asymptotes are a must. First derivative test is very useful. It's going to tell you where's f increasing, where's f decreasing, and whether you have a maximum or a minimum. And the second derivative test is going to tell you where's f concaving up, where's f concaving down, and if you have inflection points. And that's going to be key for us to sketch a graph. So if I look at the first example, it's a polynomial. I'm trying to sketch it. So it's defined, domain is everywhere, you don't have to list that. Intercepts, if I let x equals 0, y will be 6. Let's say that's 2, 4, and that's a 6. Actually, let me change the grid. That would be better. Let me make it smaller grid. Okay, that would be a lot nicer. So now, I would say the graph passes through 0, 6. That's what I know so far. Well, how does this work? First derivative test. No asymptotes. The derivative is 3x squared minus 2x minus 5. So that, yeah, the test factor, that's good. Where does that equal 0? That's when 3x and an x and a 5 and a 1. To get a 2, a negative 2, you want a negative and a positive. 3x squared plus 3 minus 5. Yeah, there you go. So x equal 5 thirds and negative 1. I'm going to test negative 1 and 5 thirds. If I test to the left of negative 1, say negative 2, negative 6 minus 2 is negative. Negative 2 plus 1 is a negative. Negative times a negative is a positive. The function is increasing. And if I pick a point between a negative and a positive, 0 is ideal. I can put that here or here. That gives me a negative. And a point to the right of 1/3. Remember, 5 thirds is what is 1 and 2/3. So let's say 10. If I put a 10 right there, 30 minus 5 is positive, and 10 plus 1 is positive. So my conclusion is that f is increasing from negative infinity to negative 1 union with 5 thirds to infinity. F is decreasing from negative 1 to 5 thirds. Now I also know that we have a local max at negative 1. If I plug negative 1 in there, I'll get negative 1 minus 1 plus 5 plus 6. That will be 11 minus 2. That will be a 10. If I make a mistake, you just need to get the idea. And the minimum, I have a minimum at x equal 5 thirds. 5 thirds cubed is 125 divided by 9 minus 525, oh no, 27. Minus 5 times 5 thirds is 25 thirds plus 6. So that turns out to be all over 27. That's 125 minus 3 times, that's 75. Minus 9 times 25, 225, and 6 times 27, I don't know what that is, 42, 24, so all of that together, you could throw that in the calculator and get negative 300, right, plus 7, 10, 407, that is 107 over 27. Alright, for that. So I know that graph holds a maximum at negative 110. Negative 1, this was 6, 7, 8, 9, 10. That's what a maximum look like. It must cross through these points. And we have a minimum at 5 thirds, 1, 2, 1 and 2 thirds. And 107 divided, let's say 107 divided by 30, right? About. So that's about 3 point sum. And minimums look like this. Now I want to take a second derivative to figure out inflection points. F double prime is 6x minus 2. And if I figure out where that equals 0, that's when x equal 1/3. There is 1/3, f double prime and f. If I pick a point to the left of that, say 0, put 0 in there. 6 minus 2 is negative. And a point to the right of 1/3, say 1. 6 minus 2 is positive. So we know that f is concaving up from 1/3 to infinity, and concaving down from negative infinity to 1/3, and we have an inflection point at 1/3, whatever that is. X equal 1/3 is about right there. So if I plug that in, that would be 1 over 27 minus 1 over 9 minus 5 over 3 plus 6. That would be over 27. That is 1 minus 3 minus, if you multiply that by 945, plus 27 times 6. 42, 12, 142. So that is negative 38 and 143. So that's a 5. 105 divided by 27. Again, about 105 divided by something's not right. Yeah, the mistake was right there. This was 1, this is 42, and that's 12 plus 4, that's 162. So 162, 163 minus, that's a 5, and that's 25. So that's 125 divided by 27. Because it doesn't make sense for the inflection point to be below the it doesn't make sense for the y value. This is 127, 107 over 27. This is 125, a bit higher. So it's about right there. So the graph is concaving up from that point on. From this point on, it looks like a parabola. It should continue on, but that's when this picks up from this point, and instead of going up, it runs on this curve. And there it is. So a bit lengthy. How about this problem? Alright, next problem. Look for domain. Well, domain is, take the denominator, you want x squared minus 4 to be bigger than 0. Well, that's a parabola shifted down 4 units. So it's best to use this. You could use a test line. Domain, negative infinity to negative 2, union with 2 to infinity. So we know at x equal 2, and x equal negative 2, we have vertical asymptotes. Alright. Now, if I look at horizontal, we're not there yet. If I look at horizontal asymptote, limit as x approaches infinity of x over square root of x squared minus 4, I notice that this is going to be dominated by x, this is going to be dominated by radical x squared, which is x over x, that's going to be a 1. Intercepts. If I let x equal 0, well, that can't happen, because there's nothing in between. The top equals 0 at 0, that's useless as well, that's not in the domain. So, what's next? Let's take the first derivative test. Derivative of the top times the bottom, minus the top times derivative of the square root is 1 over twice the square root, times by the chain rule 2x, all over the denominator squared. So if I clear the fractions, multiply by radical x top and bottom, multiply by radical x top and bottom, I'll get x squared minus 4 minus x squared over x squared minus 4. Oh, that's not squared. When you square it, you get rid of the radical, right? That's all. So when you multiply this times the 1 plus 1/2 is 3/2. So my first derivative is going to be negative 4 divided by, and this is really the square root of x squared minus 4 cubed. So here, if I do my testing, you say, okay, well, what's the testing? Negative 2 and positive 2, nothing in between. Well, if I pick a point to the left, there are no points except those two. If I pick a point to the left, say negative 3, well, the denominator is always positive, and the top is always negative, so that's going to be negative. The function is decreasing. And if I pick a point to the right of 2, let's say 3 as well, the denominator is positive always because it's an even index radical provided that's defined. Top is negative, right? So it's decreasing all the time. I missed, it wasn't making sense. So to the right, the graph is going to level off next to 1. But if I take the limit as x approaches negative infinity of x over the square root of x squared, that's what this behaves like. If x is approaching negative infinity, that will be the limit as x approaches negative infinity of x. Remember, this right here is absolute value of x, right? If x is negative, that's going to be negative x. So that's going to be negative 1. Much better. So, I get that f is decreasing from negative infinity to negative 2, and f is also decreasing from 2 to infinity. Or you can put a union if you want. Well, there's only one way f could be decreasing, right? That's the only way f could be decreasing, because if it looks like this f is increasing, that's not going to happen. And this is f is increasing, that's the only way it's going to happen. Now, I could take the second derivative. Here, I was able to figure that out, but if I take the second derivative to confirm y double prime, derivative of the top. So I'm going to write this as negative 4 times x squared minus 4 to the negative 3/2. I'm going to bring the power down, so negative 4 times negative 3/2 times x squared minus 4, subtract 1 from the power, times the derivative of the inside. Y double prime will be a positive. 2 cancel out. 12x divided by the square root of x squared minus 4 raised to the 5th power. Well, where does y double prime equal 0? Where does y double prime not exist? It turns out y double prime equals 0 and x equals 0, but that's not in the domain. So same deal, y double prime and y. We have negative 2 and positive 2. That's where this does not exist. A point to the left of negative, say negative 3. Negative 3 times 12 is negative. The denominator is always positive, so this is concaving down. And to the right of 2, say 5. If you put 5 in there, 12 times 5 is positive 60. The graph is concaving up, so we conclude that f is concaving down from negative infinity to negative 2, and f is concaving up from 2 to infinity. So as we see, f is concaving down, that is true, and f is concaving up, that is true as well. That's just confirming. I knew this was going to be the answer.